Lecture 17, The Hydrogen Atom. Reading, Zudar 12.7 to 12.9. Outline. The wave function for the H atom. Quantum numbers and nomenclature. Orbital shapes and energies. Schrödinger equation. Erwin Schrödinger developed a mathematical formalism that incorporates the wave nature of matter. Kinetic energy. The Hamiltonian. d2/dx2 x. The wave function. E equals energy, potentials and quantization, Kant. What if the position of the particle is constrained by a potential? Particle in a box. Potentially equals 0 for 0 less than or equal to x less than or equal to L. Equals all other x. Potentials and quantization, Kant. What does the energy look like? N equals 1, 2. Energy is quantized. E. Y. Y. Potentials and quantization, Kant. Consider the following dimolecule, the length of which can be considered the length of the box an electron is limited to. L equals 8, a ring. What wavelength of light corresponds to from n equals 1 to n equals 2? Should be 680 nanometers. H atom wave functions. Recall that the Hamiltonian is composite of kinetic, K, and potential, P, energy. The hydrogen atom potential energy is given by H atom wave functions, Kant. The Coulombic potential can be generalized. Z equals atomic number, equals 1 for hydrogen, H atom wave functions, Kant. The radial dependence of the potential suggests that we should from Cartesian coordinates to spherical polar coordinates. R equals interparticle distance. 0 less than or equal to R less than or equal to. E equals angle from xy plane. /2 less than or equal to /2. P plus equals rotation in xy plane. 0 less than or equal to 2. H atom wave functions, Kant. If we solve the Schrödinger equation using this potential, we find that the energy levels are quantized. N is the principal quantum number, and ranges from 1 to infinity. H atom wave functions, Kant. In solving the Schrödinger equation, two other quantum numbers become evident. L, the orbital angular momentum quantum number, ranges in value from 0 to n1. M, the z component of orbital angular momentum, ranges in value from L to 0 to L. We can then characterize the wave functions based on the quantum numbers, n, L, m. Orbital shapes. Let's take a look at the lowest energy orbital, the 1s orbital, n equals 1, L equals 0, m equals 0. A0 is referred to as the Bohr radius, and equals 0.529 a ring. 1. Orbital shapes, Kant. Note that the 1's wave function has no angular dependence, i.e., Q and F do not appear. Probability equals. Probability is spherical. Orbital shapes, Kant. Radial probability, likelihood of finding the electron in each spherical shell. Orbital shapes, Kant. Naming orbitals is done as follows. N is simply referred to by the quantum number. L, 0 to n1, is given a letter value as follows. 0 equals S. 1 equals P. 2 equals D. 3 equals F. ML, L, 0, L, is usually dropped. Orbital shapes, Kant. Table 12.3, Quantum numbers and orbitals. NL orbital ML, Ashevorb. 0101, 0201, 12p minus 1, 0, 1, 3, 0301, 13p minus 1, 0, 1, 3, 23d minus 2, minus 1, 0, 1, 2, 5. Orbital shapes, cont. Example, write down the orbitals associated with n equals 4. On n equals 4, L equals 0 to n1 equals 0, 1, 2, and 3 equals 4s, 4p, 4d, and 4f. 4s, 1 milliliter sublevel. 4p, 3 milliliters sublevels. 4d, 5 milliliters sublevels. 4f, 7 milliliters sublevels. Orbital shapes, cont, s, L equals 0, orbitals, are dependent only. As n increases, orbitals demonstrate n1 nodes. Orbital shapes, cont, 2p, L equals 1, orbitals, not spherical, but lobed. Labeled with respect to orientation along x, y, and z. Orbital shapes, cont, 3p orbitals. More nodes as compared to 2p, expected. Still can be represented by a dumbbell contour. Orbital shapes, cont, 3d, L equals 2, orbitals. Labeled as dxz, dyz, dx2y2 and dz2. Orbital shapes, cont, 4f, L equals 3, orbitals. Exceedingly complex probability distributions.